I will first introduce lattices and then speak about the different kinds of cryptographic problems that they help to solve. First off, what is a lattice? A lattice is an algebraic structure whose existence relies on order theory in universal algebra. Here we have a collection of vectors, and I can tell you that these two vectors from this origin create a base for this lattice. A base is valid if you can create all other vectors in the lattice from linear combinations of the vectors in the basis. In cryptography, in the same way that we can decide a prime is good or bad, we have a notion of a good basis and a bad basis when dealing with lattices. Typically, a good basis has vectors with small magnitude, and a bad basis would have larger vectors. Having a bad basis may slow down computations. We can also make a decision if two vectors create a basis for the given lattice or not. If you create the parallelogram created by the two vectors in the basis, if there is another vector within this parallelogram, we know from linear algebra that this vector will be impossible to make as a linear combination of b1 and b2, so therefore b1, b2 is not a basis. The first problem that is typically examined when taking a look at lattices is the shortest vector problem. Given a basis, the algorithm must find the shortest non-zero vector in that lattice. Pictorially speaking, solving this problem is very easy. Simply draw a larger and larger circle from the origin until you intersect with the first non-zero vector in the lattice. This vector must then have to be the shortest in the lattice because it is the vector closest to the origin. This algorithm runs in O2 to the n time, so if you need something faster, you will have to settle for the alpha approximation of the SVP, which returns a single vector in the lattice such that the magnitude of the vector is no greater than alpha times the size of the actual smallest vector. Depending on the alpha provided, this new algorithm can run in many different speeds. Similar to kth order statistics from your algorithms course, here we can also ask for the kth smallest vector in the lattice. Another interesting problem is asking for all n vectors with lengths at most n times the size of the actual smallest vector. This problem is known as the shortest independent vectors problem. Now that some of the problems are introduced, let's discuss how to solve the SVP problem. In one dimension, this is easy due to Euclid. If the given basis is 6, 8, clearly the shortest vector is 2 because the GCD of 6 and 8 is 2. In 2 dimensions, we would use the teaching of Gauss to find the SVP. In n dimensions, this is currently a very hard problem. The best known implementations right now for finding the exact smallest vector is O2 to the n. Now that we know how to solve the SVP problem, let's discuss something slightly related to this, which we will circle back to in a second. Consider the shortest integer solution problem. Given a matrix A with dimensions nm, your task is to find a short r such that a times r is equal to 0. All operations are done under ZQ, and the size of r must be less than some specified threshold beta. We can find a collision-resistant hash function using lattices. F is a family of functions parameterized by random full-rank matrices A in Z and Q. It takes in an R and outputs A times R all operations done in ZQ. M must of course be bigger than n log Q, or there is no compression happening. This is a linear function and are typically worthless to a cryptographer, but the domain is restricted to be a small set, and this is what gives the hardness. The hash function above is really just the short integer solutions problem. If you can find a solution in this hash function, you can break SIS. Consider a collision on this hash function. We would have r and r prime such that a times r minus r prime is equal to 0 mod q. R minus r prime is actually a solution for the SIS of A. Because r and r prime only have 0 and 1 entries, this makes them short. What we are doing here is performing a reduction on the problem of SVP. We reduce the input of SVP to an input of SIS. We then compute the SIS, and then with this solution to the SIS, we can then recover the approximate solution for the SVP problem for the given basis, and we are done.